Hello, we are employees of Burdell Inc.
My name is Emily.
I'm Nabil.
I'm Brittany.
and I'm Jaehyuk.
Today, we will speak to you about the methods and mathematical theory behind how we will characterize parameters for the DC motor provided to our company by Quanser Inc. In order to later design a PID controller for Quanser Inc. to allow their motor to reach a specified position as per the client's desired specifications. In order to characterize the motor, angular velocity and time data will be collected to later derive the motor and time constants of the given DC motor. With the DC motor, identify and describe the motor in linearly and determining the motor dead zone and saturation zone. Also, we are going to use with the time domain to find motor and time constants. So following this lab setup by considering motor depth and saturation zones. As can be seen in the bottom figure, the experiment setup follows the Quanser motor hooked up to the flywheel, where data is uploaded to a computer for further analysis. This DC motor has an optical encoder to detect motor speed using pulse-width modulation. Based on this setup, verifying input voltages from 0.01 voltages to 9 voltages are applied to the DC motor setup and used to analyze the transient response of the angular velocity output. This response will be tested both without an added mass and with an added flywheel for analysis of inertia effects on Tm and Km. Nabil will now further explain the theory behind this experimentation.
So to expound upon the procedure setup, given quantities or those voltages that are inputted in the system to see the DC motor's response. Flywheel angular velocity and time are all the quantities that are measured during experimentation and outputted from the MyRio microprocessor. The relation between these values are further investigated by plotting angular velocity versus time. This is due to the given equation to figure out omega. The steady state of angular velocity is where the angular velocity is unchanging with time and was found to be at the Tm of 0.0850. To calculate this, the equation have been used and later analyzed again in order to find the angular velocity where the time motor constant occurs. So based on the graph shown on this particular slide, it can be found that adding the additional mass to the flywheel increases the motor gain and time constant, which is an important finding in this experimentation. And now on this slide, we can see a block diagram that shows a general relation between the voltage and the flywheel mass parameters with the motor constant for time and gain when analyzing these graphs. And now Emily will walk through the responses.
Aside from the time motor constant, the motor gain, or Km constant, is also a pivotal parameter in characterizing a DC motor. This parameter is important because the motor gain shows an individual how much input voltage is needed to reach a certain angular speed or position. Creating a graph of input voltage versus a series of steady-state angular velocities previously experimentally determined, Km is found to be the slope of the linear portion of the graph. It is important to use only the data in the linear portions of this plot for doing the linear regression to find this slope, as the nonlinearities in the dead zone and saturation zones can cause bad performance due to friction or inductance of the motor. In this case, our Km for our no flywheel was 57.2732, and our Km for our flywheel was 57.4907, which which are very similar. And the beginning of our saturation zone was at 6.9 volts for both the flywheel and the no flywheel data. Dead zone ended at the same voltage for both components. From the TM and KM that we determined from these, we can use them to determine the gain constants of KP, KI, and KD for our PID gain motor control. Block diagram shows the Laplace transfer function relation between these constants, the constants, the transient response previously identified, and controller output to a desired position for the motor that was specified by Quanser Inc. Now Brittany will help to conclude everything.
So as a wrap-up, system identification is the process of using experimental data to determine modeling parameters of a system, or in this case, a DC motor. Its application helps to predict the DC motor's behavior and develop models that track. From the experimental data, it was seen that an added mass increases values for angular velocity at steady state and thus the motor gain, or Km. This will later be useful when trying to make the PD controller that will ultimately be used by the Quanser Incorporated to have its DC motor move to the desired position autonomously without human intervention or input. Thank you, and please let us know if you guys have any questions about the experiments that we've shown you today or what we would like to do in the future in order to achieve this client's desired specifications for their motor.